All right. So we're finally moving close to home. And we're going to look at solar system objects and asteroids. And your lecturer and module lead for this session is going to be Dr. Quan-zhi Ye. Quan-zhi is a postdoc at Caltech. Sorry, I'm totally out of breath. Quan-zhi is a postdoc at Caltech who's leading the Zwicky transition asteroid and solar system science. And he has lots of fun results and fun science to show you to get you motivated to work through that module.
Okay. Thank you, Nancy. Can everybody hear me from behind? Yes. Okay, great. All right. So I'm going to shift the gears a little bit. Well, not really shift the gears because I know Melissa just talked about asteroids, which is fascinating. I will talk about asteroids. I will start with a little bit of a dark story of asteroids. If you ask my colleagues, astrophysical colleagues sitting there, and you ask them whether they like asteroids, they'll probably say no. It's okay. Well, and this is because, well, as some of you may know, asteroids are a pretty infamous nickname. Wormy in the sky. Why do they have such a bad nickname? Well, this is because they are a very significant source of foreground contamination. To illustrate that point, let me show you a figure on the left. Well, I know it's pretty bright. You know, we astronomers want to work in the dark, but you know, use some of your imaginations and pretend you see a lot of objects there, which they are. But this is a Hubble Space Telescope image of galaxy cluster Abell 370, if I remember correctly. And here you see a lot of curvy streaks in the field. And guess what they are? They are not cosmic rays. They are not image artifacts. They are actually asteroids. And apparently, if you're an astronomer not interested in asteroids, you probably hate to see them, right? And you probably wonder why they look curvy and why you see it looks like they are, you know, there are a certain number of them. You see you have 4 here. You have, well, these 2 are probably the same. And yeah, you have 2 here. And the reason is that is because Hubble Space Telescope is orbiting the Earth. So what you see here is a combination of the asteroids' motion. Well, we see the motion of them. If you take a picture, if you have some observational astronomy experience, if you take a field near the ecliptic belt, you take several pictures over, let's say, 30 to 60 minutes, you'll see some moving dots, and those are asteroids. Why they move? Because they're close to us. They are in the solar system. They're close to us. So you can see them moving. And also, the telescope is orbiting around the Earth. So here, this is actually coming from images from different HSD orbit. And I think this is mostly due to the motion of the telescope, but also in part due to the motion of the asteroids. So, and especially if you work in transient science like supernovas, you take a picture, you see a bright dot near a galaxy. Well, it might not be something that you were looking for. It could be asteroids. So I think now we are in a much better shape than, let's say, 30 to 40 years ago, thanks to a number of solar system surveys. We spent quite a number of time, effort, and also money documenting all the asteroids in the solar system. But back 30 or 40 years, most of the asteroids in the solar system are not known. You don't know what they are. If you take a picture, dot there, what you can do is you take another picture in another 30 minutes and see whether they move. So on the right-hand side, this is a top-down view of the solar system. All the dots here are asteroids, different type of asteroids. Red dot here, let me start with the circles. The circles are the orbits of major planets: Jupiter, Mars, Earth, Venus, Mercury, and the Sun. Earth is here. All the red dots here are near-Earth asteroids, Main-belt asteroids, and other groups of asteroids. So as of last night, there are something like 800,000 known asteroids. Most of them are brighter than something like 20 magnitude. So if you have a decent size aperture telescope, 1 meter size, take some exposure time, you're able to reach that. All right. So, and one last thing I want to say is we talk about asteroids all the time, but a very small number of moving objects are also comets. Their ratio is more like 99 to 1. So 98% of the small bodies, moving objects you see asteroids, there are also a small number of them comets. And these 2 classes of objects, we call them the small solar system bodies. So let's start with the definition. So what's the definition of small solar system bodies? So according to the resolution passed by the International Astronomical Union 2006, some of you may have an impression of that because that's the meeting that basically kicked Pluto out of the major planet class. All it says is that any solar system object that's not a planet, not a dwarf planet, not a natural satellite, will be a small solar system body. This is a pretty obscure language. So let's put it another way. This includes most of the asteroids, comets, large meteorites, large objects in the outer solar system. So why do I say most asteroids? Well, because some of the largest asteroids, like Sirius, the biggest object in the asteroid belt, are in fact a dwarf planet. So in a rough sense, if you wonder what they are, in a rough sense, anything larger than dust. Here, by saying dust, we don't mean the dust, on the floor, very small, you can't see them. When we say dust, we mean something like 1 meter size. This is a pretty arbitrary definition. And if they're smaller than 1,000 kilometer in size, this has some, physical background of it, but I won't go into great details of that. You can come to me after the lecture if you want to know. Anything within this class, except for natural satellites, will be defined as a small solar system, asteroids or comets. So still, it's a little bit obscure. So here I show you a picture, a collection of asteroids, actually small bodies that have been visited by spacecraft. On the lower right, I show you a 2-scale map of the San Diego area, just to give an idea how big asteroids are. I assume most of you are right by air, so here I show the 2 marks here. This is San Diego Airport. This is SDSU, where we are right now. And on the left-hand side, a bunch of asteroids. This is one of the largest objects that have been visited by man-made spacecraft. It's very small here, but it's asteroid number 21, Lutetia, visited by the Rosetta spacecraft in 2010. Most things on the right, they are much smaller. Some of the cometary nuclei, and this is a little bit bigger. And there are 2 active missions orbiting around asteroids now. One is the Japanese spacecraft Hayabusa 2, orbiting Ryugu. If you can see here, it's very tiny. And another is the NASA spacecraft OSIRIS-REx, orbiting Bennu. They're also here. So the takeaway from this is most of the objects, we only have a few objects at this size in the main asteroid belt, but we have 1 million objects at this size in the inner solar system. So the idea is that most of the asteroids you'll see are much smaller. It's very small, each of them can be probably fit into the San Diego metro area. And Bennu is the smallest object that the human spacecraft ever orbiting to. So this is also 2-scale. This is a map of the SDSU campus. I believe most, if not all of you, what's the name? Dora Aho? I think it's somewhere down here. I think we are somewhere here. This is the size of Bennu, something like 500 meters in diameter. So if you walk from the dome to here and then back, and basically distance you can still in the asteroid Bennu. So you can see that asteroid is really, really small. And now, astronomers, there are 3 classes. There are 3 general types of astronomers: observers, dynamicists or theorists, instrumentist. So if you're an observational astronomer like I do, you want to get a sense of what small solar system bodies or asteroids and comets are like. So here are some figures. On the left side, this is what a major planet, Jupiter, looks like. If you have to like stargazing, if you go to a star viewing sessions, looking the skies through a telescope. This is what Jupiter's look like. One of the major things that you can notice is that it has a disk, right? And asteroids, they mostly they don't have a disk. I should say that 99.9% that you work on asteroid data, unless you work on spacecraft data, unless you work on AO adaptive optics data, they always look like a dot. And here it's a time lapse of images. You can see asteroids moving in the sky. This is a time lapse. It's taken over a time of something like 40 minutes. And another fun thing here is the name asteroids. Apparently come from ancient Greek. I don't speak Greek. I hope some of you can tell me how this should be pronounced. No? Okay. But it means star-like. So this is a very precise name. They look exactly like star, just like a star in the sky. And this is why, other astronomers hate asteroids, because they confuse your objects. And for comets, also come from ancient Greek. That means wearing along here. So on the right-hand side, I show a picture of two comets. A small number of comets got pretty bright. They can become a very fascinating look at. Like this is a comet Lovejoy. That was in about 10 years ago. And notice that this is taken by a wide field, digital camera. So that means, if you go out and if you look at the sky, you see a big object with a tail in the sky. It's pretty fascinating. But most of the comets, they're small and faint. This figure is Comet Palomar, the first comet found by ZDF that was found a few months ago, and at a magnitude of 18. And you can see that the comets here is a pretty fuzzy, small object. The tail is no more than a few arc seconds long. While for this one, this should be Comet Magnot, not Comet Lovejoy, but Comet Magnot. The tail is something like something like 20 degrees long, so it's pretty impressive. Of course, with observers, you want to go a little bit further than just detect asteroids. There are a whole bunch of other things they can do. One thing that you can do is to take a spectrum of it, just like other things, like supernovae, like variable stars, like other fascinating things that you look at, that you can find in the sky. So therefore, if you take a spectra of a number of objects, like thousands of asteroids, and then you try to get some idea of what they're like, you'll quickly realize that there are 4 broad classes of asteroid types. Two of the broadest classes are known as C complex, or S-type and C-type. And S stands for stony. This tells you something about the composition of asteroids, and the feature of that. I say a bit of the labels in case you can't see it from the back. Can you guys see what the small numbers here from the back? It's difficult? Okay. So this is 2.9 micron, and this is 0.5 micron. So it's basically optical to near infrared. Okay? Make sense? All right. So the features of S-type is that they got a pretty reddish spectrum. This has something to do with the surface properties. And also, and then the other one is a C-type. C stands for carbonaceous, and they are not as red as the S-type, as you could probably see. Like B-type, a subclass on the C-type, even got a bluish spectrum. So it's pretty interesting. But the takeaway message here is the C-type and S-type. The main difference in their spectra is that S-type is pretty red, and C-type is not as red. And you also get X-type. Well, X means that it doesn't mean anything. It just means that it doesn't belong to S and C. And people got confused in early times. Astronomers got confused because they got a spectrum somewhere between C and S, but don't fall into any either of them. There are other smaller end members like D-type. That's super red, and people think that it's because they are died cometary nuclide, rich in water ice probably. And another interesting thing type is the V-type. People think that it's a fragment of asteroid Westad, one of the largest asteroids in the main asteroid belt. And if you like dynamics, then you can look at this plot and figure out the general characteristics of asteroids. So I'm pretty sure all of you have seen this plot, or any plot like this plot somewhere. Top-down view of the solar system, or actually we have this figure in the opening slide, right? So most of the asteroids that we know are in the main asteroid belt. They are between the orbit of Mars, Jupiter. About 90% of the known asteroids are in the main asteroid belt. We also know that there are near-Earth asteroids. They are defined as an asteroid with a perihelion distance smaller than 1.3 astronomical unit. One astronomical unit is average distance from the Sun to Earth, of course. And there are some children, not children. Children asteroids. Most of the children asteroids are Jovian children. They are children asteroids of Jupiter. Children asteroids are the asteroids that share the same orbit of major planet. Jupiter has a lot of them. Saturn doesn't have because of some weird dynamical interactions between Jupiter and Saturn. Neptune also has a small number of them. Earth only have one of them, although people think that there should be more. And Venus, I don't think Venus have it, but Venus have some quasi-children, which people are also interested about that. And another thing about asteroids and also comets here is that some, all of them are somewhat dynamically controlled by major planets, mostly Jupiter. Objects in main asteroid belt, they are pretty stable. They have been there for billions of years, like near-Earth asteroids, because they cross the orbit of Earth, and sometimes, and most times Mars, and sometimes Jupiter. They often have a close encounter with Earth and also other major planets, making them dynamically unstable. The dynamical lifetime of near-Earth asteroids is something like a few million years or something like that. On the right-hand side, this is the orbit of comets, and you can see that almost all comets, except for a few, I think I can count it with one or two hands, they always cross the orbits of major planets, so their orbits are pretty unstable. And okay, so if we combine our spectral information with dynamical information, we get something very interesting. So this is okay, so let me describe the figure. So this x-axis is distance from the sun, and this is basically what we saw the last slide, except that you take a cut from the inside to the outside. And the y-axis is the relative number of asteroids in different types. And here you can start seeing some features. So for example, C-types, they are like about 3 astronomical units from the sun in the main asteroid belt, and also S-type closer to the sun. And we also got a large number of D-types if we go further from the sun. There are really a lot of information in this graph. I guess I could probably spend the rest of the day talking about it. But the key information here is that by doing this kind of mapping in the solar system, we get an idea of the distribution of different materials in the solar system. And this is actually one big thing in asteroid science. Okay. All right. So we spent the first few slides talking about what asteroids are, their definition, how big they are, and how, some knowledge of it. And the next thing we want to know is why are they important and why are they interesting? I will start with something that I think is most interesting is because asteroids and also comets, sorry, I keep missing thing, is that they contain primordial material. Why is that? Because they're small enough. They don't like major planets like Earth. They don't have this differentiate effects. Differentiate means that denser materials sink to the center and lighter materials floating on near the shell. Asteroids are too small, so they don't have that. And this means that if we want to study, we want to have an idea of what the solar system is like in early times, we go to small bodies. They don't mess you around. You can just go there and see what's on it, and get a sense of what materials in the early solar systems like. Most important things, there are two, waters and organics, because they're life essential. On the left-hand side, this is a figure of the so-called DH ratio. These are the isotope of hydrogen. And from this, we get an idea of the formations of water molecules and different parts in the part of the planetary disk. So the interesting information from here is that in early times, people think that the water on the Earth comes from comets, because comets are rich in water ice. Why do we know that? Well, we just see that comets have big tail, right? And the reason they have big tail is that they are rich in water, ice, and other volatiles. And when they approach the sun, these materials go heat up, and they start sublimating and leave the dust on the surface into the interplanetary space. And from the distance, you see the big tail. And this is why we know that there are volatiles on it. So because they're rich in volatiles, people used to think that most of the waters on Earth come from comets. But then people start measuring the DH ratio of different objects and realize that comets, shown the green dots here, actually have a pretty different DH ratio compared to the Earth, shown here. And astonishingly, asteroids actually have a much closer DH ratio to the Earth. Well, I mean, when we talk about asteroids, you're probably thinking about asteroids just rocks. But actually, some asteroids, and especially certain types of asteroids like the C-type that we just talked about, have water molecules trapped in the cracks, well, not in the cracks, but in the material. They're not as water-rich as comets, but they do have comets. They do have waters. So it's a very interesting discovery. This means that most waters on Earth, if you buy this theory, likely come from asteroids rather than comets. I should point out that there are a few comets here. This reads Jupiter family. There are certain group of comets also have DH ratio comparable to the Earth. So on the right-hand side, this is a high-resolution spectrum of a comet. This is a radio observation. It shows you the emissions of some complex molecules in the comets. So the idea is that most of the organic materials, life building blocks on the Earth, likely come from comets. And by studying asteroids, comets, we know about the waters and also organic contents in the solar system. And the next, the footprint of planetary migration. And one of my favorite example is the existence of Oort cloud. So Oort cloud, it's a hypothetical spherical structure in the outer solar system, but we have some evidence that they exist because when we observe long-period comets, comets with aphelion distance, aphelion point in the outer solar system, they seems to be pretty isotropic rather than distributed along the ecliptic plane. So, and why is that? If you look at, if you look into exoplanet images, you realize that how planet systems are formed. You have clouds condensed in the disk, and then you have disk, the center part condensed into a protostar, and you have major planets forming along the disk. So why do we have this spherical structure in the other part of the solar system? Well, now we understand that the reason that we have a spherical structure in the other part of the solar system is that there is in the early times of the solar system, major planets are not where they are right now. Like Jupiter, it actually moved. Jupiter actually reached a location much closer to the sun than it's right now. It's actually around the orbit of Mars. And this so-called planetary migration scattered a lot of planetesimals, shown as a small dot here, in every direction. And this kind of dynamical scattering is pretty isotropic. And this is why we have a large number of small planetesimals in the outer part of the solar system in the pretty spherical structures right now. So by studying and by looking at the distribution, orbital distribution of small bodies, you can actually figure out what has happened in early times of solar system. And another thing is, remember the figure that I just showed, a lot of C types at 3 AU, S types at 2 AU, and more D types at 5 AU. This is like mixing of materials. Of course, in the early time of the formation stage of the solar system, you don't have this kind of mixing. But the result that you're seeing right now are the distribution you're seeing right now is a result of a planetary migration. So by studying the distribution of different materials, we get an idea of what's happened in the early time of the solar system. Okay, so third, connection to exoplanetary science. Exoplanetary science is a pretty hot topic right now, but we are starting from afar. And by looking at solar system materials, we put exoplanetary observations into context. So this is one of the very nice images of a Fomalhaut system taken by Hubble Space Telescope. At different times, images taken at different times, you see a tiny dot moving over there. And this is a planet in that system. But what I like about this image is also because ring structure. This ring structure, I don't remember, there is no scale here, but I think this is something like 30 astronomical unit. So this ring, you might think it as like an asteroid belt in the Fomalhaut system, but it's really like a Kuiper belt in that system. And of course, with current technology, we can't resolve individual particles in that system, but by studying the Kuiper belt in our own solar system, we get an idea of what the materials in that Kuiper belt systems like. So it's pretty amazing. And fourth, of course, I guess a lot of you know that is the Planetary Defense. If you doubt that, then go to museums and ask about dinosaurs, what they think about asteroid impacts. And this is the meteorite crater. It's pretty amazing if you haven't been there. and planetary and this is actually one of the main reasons why we have telescopes working every night, ZDF included, because asteroid science is one of the science goals of ZDF, and also other telescopes actively looking for asteroids in Earth inbounding course. And this actually happens a few times. That we have seen we have detected asteroids, and then it hit the Earth a couple hours later. So here, this is an asteroid called 2018 LA. This has no reference to the city of LA, but it simply means that L is the first half of June, and A means this is the first asteroid found in the first half of June. And this asteroids were only found, I think, something like 9 hours or 8 hours before the final impact in the country of Botswana in southern Africa. And we also have done a lot of practice or just rehearsals. What will happen if a large asteroid is found in an Earth inbounding course? So on the lower right, this is a slide from the Planetary Defense conference that was held early this year. This conference, PDC, is held every 2 years. The conference this year was held in the University of Maryland. And this shows you the simulated damage predictions if a 100-meter size asteroid hits the central park of New York. So I'm pretty sure the folks from New York won't like it very much. So the fifth is space industry. You've probably seen some news reports saying that we have found $1 billion or $1 trillion or whatever $zillion asteroids because there are platinums on it. But I can tell that that's probably 99% nonsense because what we really are talking about right now is how to use waters on asteroids. Why is that? Because it's very expensive to send waters from the Earth to space. So if we can mine waters from asteroids, we just mentioned that water on Earth likely come from asteroids. If we can take the waters from there, then it can save us a lot of cost to ship the water into space and help folks to go in the deeper space. All right. So how do we study? Well. Oh, sorry. Turns out my just crashed. All right. So how do we study? So one thing. So of course, if we want to study asteroids, we first need to know where they are. 30 years ago, we don't know where they are, so it caused a lot of trouble. And let me see. Excellent. I make it the first trial. So. There are a number of sky surveys looking for asteroids every night. Most of them are found at NASA. Actually, NASA found surveys has found 98% of all the near-Earth asteroids to this date. This is a map. There are a few asteroid surveys that you need to know. The first will be a Catalina sky survey run by the University of Arizona. That's a little north of Tucson. They have a pair of telescopes, 1.5 meter and also 0.7 meter. And ZDF, not strictly an asteroid survey, but we are also working on asteroid right now. And another pair is a Pan-STARRS survey, 2 telescopes, 1.8 meter in Haleakala of Hawaii, and also Atlas survey, the pair of 0.5 meters, one in Haleakala in Maui Island, and also another in Mauna Loa in the Big Island. There are a few other planned surveys. LST is coming online in the next couple of years. Atlas is expanding to South Africa, and also SST, the Space Surveillance Telescope, has some military backgrounds, currently being moved to Australia, and the Europeans also thinking about being up their old asteroid survey telescopes. There's also another one in the space, NEOWISE, that look for asteroids in the infrared. So there are several ways to detect asteroids, and also this is somewhat related. This is somewhat related to the hands-on module that we have in like 20 minutes. So the first will be connect the dots, because we just mentioned that, the dots is moving. Crash again. So the first will be connect the dots, because we just mentioned that, astrophysicists got pissed off by asteroids because they just look like other stars. But for asteroid scientists, if you take images at different time and you just blink it, you will see asteroid moving. Let me see if I can go back to. they are moving. Excellent. So the idea is that you take a couple images, 3 to 5 visits. You don't want to take 2. Theoretically, you can work with 2, but the problem is that then the image artifacts and other hot pixels and stuff will mess around with you. You want to have 3 to 5 visits over about 1 hour to review the motion, and you write software to detect them and try to just connect the dots. And this idea is used by most surveys because it's pretty simple, and by this way you can detect about, I would say, 99%, if not more, of all the asteroids. And another very useful, the near-Earth asteroids, but pretty tricky, is called the streaks. Why is that? Asteroids that are close enough to the Earth, something like within a few lunar distance to the Earth, because they're moving so fast, they will trail even under a very modest exposures, like 30 seconds of the ZDF. But they're interesting because they're very small. They are only bright enough when they are coming closer enough to the Earth, and therefore trailed. And you won't be able to see them if they're far enough. They're like dots, but they're too faint. They're difficult to detect because they trailed, and if you have with source extractor, you know that trail objects isn't very easy to detect. But at ZDF, we have a deep learning model, or you'll see it in the hands-on sessions, that are used to detect streaks. Streaks, but apparently, people are paying more and more attention to streaks, like a 2018 LA that I just mentioned. When it was discovered, is actually a trail object, as shown on the left hand. You make an intact there. This is a safety camera. You can see the impact of asteroids in the form of a very bright meteor. And a group of astronomers were sent to the site and then recover a little piece of asteroids. Another interesting thing you probably heard about is the interstellar objects. Why they are trailed? Because they are interstellar in nature. They are in unbound orbits. They travel very fast, and they trail. So on the left-hand side, you see this is a discovery image of Oumuamua, the first and the only known interstellar objects that found to date by Planetary survey in 2017. Can you guys see it from the back? It's really faint, but no, we are astronomers, right? We should be able to see it. Yeah, it's trailing in this direction. And this is a follow-up image by CFHT. The asteroids shown as dots because we are doing a non-sidereal tracking, and all the stars in the background are trailed. And just by the way, you probably heard about Oumuamua being a alien spacecraft or something like that. I should say that there is only one explanations, and there you can explain the appearance of this object by purely natural causes, like it's probably just an ordinary rock coming from another planetary system. So yes.
So in the previous thing, what are the faint dots below that? Are those all asteroids?
You mean this one?
Yeah.
They're likely image artifacts. That's a good question. I think they are image artifacts. Yeah. So the other that we mentioned is to take a spectrum of asteroids and understand its type, because this tells you something about the properties of the surface. And you can also do a light curve study. Melissa just covered that. Thanks, Melissa. And you can also observe in the infrared. This will tell you something about the physical properties of the asteroids. And you can also do something like that's called as the phase angle study. The idea is that you observe asteroids at different phase angles. Phase angle is the angle between the direction to the asteroid and the direction to the sun, and see how you reflect things. And from this, you get an idea of the properties of the materials on the surface of the asteroids. And you can also look at dynamics. This is also very interesting. If you do a plot of the distribution of number of asteroids with as a function of the this distance to the sun, you see some big gaps at certain positions or at certain positions. And this is because the dynamical interactions between asteroids and major planets like Jupiter. The idea is that asteroids that are in this gap very dynamically unstable. They are quickly kicked out of either the solar system or the inner part of the solar system through a dynamical interaction with Jupiter. And very interesting, what I found really fascinating is that you can see similar features, similar structures like this in exoplanetary observations. So here are some ARMA, I think there are ARMA observations of some protoplanetary disks, and you see some gaps in there, and it's quite possible that some, if not all, probably a number of these are created by unseen major planets in the planetary in these systems. And also, you can study evolution also and state of asteroids. I have been mostly mentioning asteroids and keeping comets at the bay, but actually, asteroids and comets, they are not like black and white. They're actually, asteroids can become comets if, for example, they are being impacted or they disintegrated, and comets can become asteroids if they use up their water ice, if they use up their water ice storage. So on the left hand, and this is known as something called active asteroids. You can see this object in the asteroid-like orbit, but it becomes a comet. And by taking images at different times, you can see how different components interact with each other, and the entire system becomes fainter. And also for comets, similar things that happen. You sometimes see comets that suddenly stop. They suddenly cease to be active. They probably use up the water ice near their surfaces. They can be activated, or sometimes they just disintegrated. And some asteroids, comets, have a more dramatic ending, like the Shoemaker-Lewis 9 in 1994, make an impact to Jupiter. And we also see comets that, they are not impacting the sun, but they are so close to the sun that it just got evaporated. So the last few slides, what's up for the future? This is a little bit of like a personal opinion because a lot of interesting things happening. But I think the most interesting topics in the next few decades in this area, for the one, it would be to improve the completeness of a small near asteroids, like 100 meters of size or less. And this is one big reason why at ZDF we are actively developing this software package to detect trail objects, because they represent some of the smallest near-Earth asteroids that can be ever detected. On the left-hand side, this is a completeness chart of near-Earth asteroids by size. X-axis is the size. This is 10-meter size, if you can't see it from the back. This is about 1 kilometer in size, so-called continent killer, and a few kilometers in size, that would be the Earth killer. But the idea is that we are pretty complete down to maybe something like 400 meters in size, but we are maybe less than 20% complete at something like 100 meters in size. So for the next few years, or next decade too, we want to improve our knowledge of the asteroids in this region. And we hope that the strict detections at ZDF, and of course LSST, and also the NeoCam, next generation space asteroid hunter, will help us to achieve that goal. And another is the active asteroids that we just mentioned, because there could be a number of reasons behind the activities of these asteroids, like they could have water under their surfaces. They are probably becoming comets because due to their rotational evolution. There are a lot of unknowns there. And probably something that worth a note is that asteroid Bennu, the spacecraft OSIRIS-REx that is currently orbiting it, is also found to be an active asteroid, although ground-based telescopic search will turn out negative. And you can see a lot of particles, each something like 10 centimeters in size, are being released by these asteroids. And as the last slide, I promise. And one of the things that I found pretty fascinating about asteroid science is it's astronomy, but it's also other subjects. This is why we call it the planetary science, and planetary science is a very interdisciplinary subject. We need astronomers, we also need geologists, we also need atmosphere science if you are interested in major planets. It's a combination of a lot of things. So in planetary science and asteroid science, we study asteroids not only by telescopes, ground-based or space-based, not just by model, but also by spacecrafts. So this are the missions that has been launched or currently at their targets or about to be launched in the next decade. So we'll see how many missions we have then. We have Dawn mission that just finished exploring asteroid or dwarf planet Vista. Dwarf planet Sirius and asteroid Vista. We have Hayabusa 2, the Japanese mission, asteroid Ryugu, OSIRIS-REx. The DART mission will conduct an experiment for well, it's short for Double Asteroid Redirection Test. So the idea is that we're going to bombard an asteroid and see how good we can do about it. Destiny Plus is another Japanese mission. There's a Zhenghe mission of the Chinese, Common Interceptor of the Europeans, another small set mission to another pairs of asteroids, Lucy mission to Jupiter Trojans, and Psyche mission to metallic asteroids. And this is and besides all this, spacecraft investigations, we also have a number of ground-based missions, except NeoCam. All of them are for astrophysical studies, but they're also excellent tools for studying asteroids, like LSST and WFIRS, and also spherics. All right, so that's all I wanted to say. Thank you. Any questions about all the materials before we move to the hands-on sessions? Too much stuff? Okay, thank you.